So everyone, my name is Matt. Today we're talking about deploying Dask. So I've worked on Dask for a long time. I'm one of the maintainers, and oops, sorry. Yeah, I'm one of the maintainers, and a conversation I often have is I sort of talking to someone and say, "Hey, use Dask. It's easy, it's fun," and someone says like, "Yes, I love Dask. Go Dask. Hopefully, you are also this person." If you're not, if you've never heard of Dask before, this is probably not gonna be the right talk for you. You should like leave this session, go off to YouTube. There's thousands of talks on Dask today. Mostly today, we're gonna talk about the next question, which is how do I deploy Dask securely or in a nice, robust way? So what comes after you say you really like Dask? How do you actually get it running in an organization? This also applies to any other distributed computing framework like Spark or otherwise. So I've done this a lot of different people. Eventually made a company, Coiled, which makes it really easy to deploy Dask. And I say, try Coiled. It's easy and cheap. People say, no, I'll do this myself, even cheaper. And this is, an interesting conversation I have. And mostly my response to this is that it might not be as easy as you think. Deploying distributed systems inside of large companies is challenging. And so this talk, I want to give a talk which is really about this question. It's a challenging thing to deploy a distributed computing framework robustly inside of an organization that is both sort of safe for IT and is also pleasant to use. It's often you get sort of one or the other, but not both. So this is what I call a classic iceberg problem. It seems really small at first. You think, I can deploy things. I know how to use Kubernetes. I know how to use the cloud. And so it seems really small, but as you get closer and closer to the problem, it actually gets pretty big. And I've talked to a lot of people who sort of run into this sort of like the bottom of the iceberg. So I want to educate folks about what the sort of the bottom of the iceberg is. Deploying distributed systems is not just borrowing machines from the cloud or HPC. It's, can I connect those machines securely? Can I turn them off reliably? Can I manage costs? Can I ship software to those machines? And that's where things get a little bit complicated. So we're going to go through and sort of learn a little bit more about a lot of the bottom of the iceberg topics. Hopefully this will help you as you're thinking yourself about how you deploy systems yourself. So this talk will be in 3 parts. There'll be a Dask example. I would like to start with a sort of a more flashy example. Then you're going to learn more about the problem, about that bottom of the iceberg. And then we'll learn about some solutions. So I've got my own solution that I pitched, but I also sort of sent out some emails to other people who have similar solutions and try to get some information about a few of them. So hopefully you can see some other ways which will have solved this kind of problem. So first, let's look at an example. So a couple weeks ago, was looking at the work of my colleague, James Bourbeau, and James is trying to get Dask integrated to a library for hyperparameter optimization called Optuna. It is a cool library made by the folks at Preferred Networks. Makes it easy to do hyperparameter optimization. We see a lot of people using Dask and Optuna together. We wanted to make it easier. And so I wanted to try out James's work. And so I downloaded Optuna, I cloned it, I checked out his branch, and I installed it locally. And I'm going to ask for a Dask cluster that runs that software. And we're going to sort of get a bunch of machines in the cloud. I'm using Coiled here as our service, but you could use lots of things to do this. And we're going to play with an example, and we're going to refer back to this example frequently in the talk. And if you are watching along, you might guess the kinds of things I'm going to talk about. So what's going on here? So I'm asking for 20 machines with 2 cores each using the software I have locally. And it has, notice I've got like a locally edited version of Optuna, and it's packaged that up. And then it has provisioned a bunch of machines. So there's 1 machine still provisioning, but the 19 the rest are done. So when I say provisioning, I mean that we are asking the cloud, AWS in this case, for 20 machines of 2 cores each. Looks like it's been giving us T3 medium instances. Those machines then booted. So they're installing Ubuntu, they're turning on, the power is coming on, I'm getting access to them. And now those machines are on. Those machines have been rented. It took about 20 to 30 seconds for me to get those machines. Now I'm installing software into those machines, right? I am installing XGBoost, I'm installing Optuna, I'm installing Dask, I'm installing Python. Now I've got my machines. And so I can go and I can play with that system. So from my MacBook here, or actually on a Mac Mini, I'm connected up to that cluster. And I'm going to use, some code that a colleague of mine at NVIDIA had written to do sort of XGBoost training. And we're going to see that, Dask and Optuna and XGBoost are all playing together, and I'm sort of doing lots of things in parallel. If you've seen a Dask talk before, you know how to interpret these graphs on the right. But, I'm doing lots of machine learning stuff in parallel on these machines I just rented. And then when they finish, I'll get some nice results. So I'm able to sort of experiment here with my colleague's work, with James's work. And it was nice. I'm able to sort of like play with something live and see how it performs. I'm seeing it perform nicely. I actually like that this is pretty easy. The code I had to write to do hyperparameter optimization was not that complicated. Now that it's done, I can go and I can, look at some Optuna things. I actually don't really know how to interpret these plots, but maybe you do as a machine learning person. So cool, I got a thing, it worked. I can report back to James that it worked well. I then went and looked a little bit at performance. And I noticed that we're only spending a very small amount of our time actually training XGBoost. And most of our time is doing like administrative Optuna coordination work. And so this concerned me. Like I'm trying out this development workflow, and it's actually not as good as I thought it was. I was able to dig a little bit deeper. And so I sent James a message, right? This is a couple weeks ago. I said, hey, James, I'm trying this out in the wild, and workers are working something that doesn't seem quite right. So I sent him actually like a performance report. So he can go and he can look at the same thing that I just did, and he can see that same profile. I then, like 20 minutes later, I like put a print statement into my code and ran it again. I said like, hey, like I'm seeing things that are kind of strange. So this all happened a couple weeks ago. James made some changes, and I'm happy to announce that things are now merged. So Optuna now has Dask support, or it will have Dask support in the next release. But this gives you a sense for how people operate in the wild with something like Dask at scale with normal code, right? This isn't a canned example. This is actually like a pretty live example. So that's my example. We're going to refer back to this a few times as we're thinking about all the things that needed to exist in order for me to be able to do this well. So now I'm going to switch to... So again, the saga is in 3 parts. One, a Dask example we've just seen. We've seen Dask do machine learning at scale on the cloud. It was great. And now we're going to learn about all the problems of setting that up. And that'll be the bulk of the talk. And then we'll see some solutions, some things that solve some of these problems. So what kind of problems are we looking at? What's the bottom of that iceberg? We'll talk about borrowing machines, installing software, connecting to those machines securely, observability, and user and cost management. I'm going to go through these things as quickly as I can, so we have some time for questions at the end. So, borrowing machines. You're always going to rely on some kind of resource manager to borrow machines. You could install Dask manually on a bunch of machines you have in your basement, but you probably don't want to do that. You're probably going to rely on some other technology like Kubernetes or the cloud or an HPC job scheduler. And typically, what you're going to do is you're going to, in Python, ask for a number of machines, a number of CPUs, a number of amount of memory, and then some Dask library is going to translate that into some sort of request for the underlying job manager. So here, if I'm using Dask Kubernetes, I get a Kubernetes YAML spec. If I'm using something like dask-cloudprovider, which talks to the cloud, I'll use some kind of BOTO or EC2 or AWS API. If I'm using an HPC job scheduler, I'll just get translated to a job script. If you're using one of these systems, one of these 3 things was familiar to you and the other 2 weren't. But what's nice about Dask is that these are all the same API and they have different backends. So it's easy to migrate from, say, HPC to cloud. And we saw this also with up here, right? I asked for 20 machines with 2 cores each, and I got a bunch of T3 mediums, right? So no matter what system you have, Dask can run on that system, and that's nice. And Dask runs on like lots of systems. Like if you're using DigitalOcean, or if you're in Europe using Hetzner, if you're on MPI, there's a Dask system for you. But this is just the top tip of the iceberg, right? Just like borrowing machines is the easy part of deploying Dask. And even this gets pretty complicated, right? Like often people don't just want CPUs and memory. They want, they're using disk, and they find that the disk that its default is really bad. They want fast SSDs, or they want GPUs. First they want T4s and they want A100s because they're doing training. or they're doing spot because they want to reduce prices and they want to select a certain availability zone in a certain region. This gets pretty complicated pretty quickly. And we often have people who just like set up Kubernetes and assume they'll be fine. And actually things get pretty hairy pretty fast. Moving on, that was borrowing machines. Let's talk a little bit about installing software. So on my machine, I've got some libraries. You saw I've got XGBoosts. I was playing with Hubtuna. I was playing with Pandas. Now I've got to get those machines over a wire to all of my machines running Dask somehow, right? And how do I do that? And this can be a variety of different things that I care about moving software. It can be the operating system. Actually, this actually honestly doesn't matter that much. Like I'm using a Mac here and I'm connecting to Linux machines and everything's fine. It can be system libraries. It can be Python itself, right? Do the versions match? If I've got Python 3.11 locally and Python 3.7 remotely, that probably doesn't work very well. There's things like pip and conda packages, which most systems think about. So my own custom code, my private code, be it private GitHub packages, locally editable packages, right? We saw that I was playing here with this like Git version of Hubtuna. So there's lots of different sort of levels of software that I need to send over and make sure that they match. And these can be kind of challenging. It's especially challenging these sort of bottom bits that are a bit more rapidly changing. Some systems don't handle these well. And this is actually pretty important to give me this kind of rapid development cycle that I'm looking for. So any system you're going to use will have to solve this in some way. And different systems handle it in different ways. If you're on an HPC, like a big iron system like IBM, or you're running Slurm or PBS or Grid Engine, you probably have a network file system. And this is actually magic. Like this actually works super well. There's like a bit of software that makes sure that all the machines see all the same software everywhere. This is a really good development experience. These systems are usually really old and they're being sort of retired, which is a shame because this is really the best development experience. A shared network file system everywhere solves lots of problems. For the rest of us, there's Docker, and Docker tends to be the de facto standard that we see to ship software around. Docker is great. It's a great technology. It does introduce this sort of like this piece in your development cycle where you're editing a Docker file, you're building a Docker image, you're pushing it out to a container repository. And you do that every single time you make a change, right? And so I mentioned that I was sort of in my development cycle, I then like added a print statement into my code to see if something was wrong. And I ran the experiment again. And if I have to do that every time I make a change, this gets challenging. Docker is a really good tool for stability across time and across machines, but it's actually a pretty bad tool for dynamism. It's not very good for sort of interactive workflows. So anyway, as you're thinking about installing software, this is probably the second biggest thing people think about after borrowing machines. And many people think about these sort of top pieces. How do I get the right conda and pip packages onto the remote machines? And the answer is usually Docker. But people should also think about, and you're going to need to think about, how do you handle this bottom part of that stack? Local packages, local scripts, dynamic functions. So software distribution is still an open problem. There actually aren't very good solutions to this yet. I actually want to point briefly to a couple pieces of technology I like. Conda Store here at the link at the bottom, made by the folks at Quansight. I'll talk about it briefly later. But it's a cool self-contained system that helps to deploy packages. And also Prefix. The developers who made Mamba, the Conda alternative, recently started a company. It's very new, very young. I want to take a look at them. So they'll sort of solve something in the space in the future. So, moving on. Network access. So we've borrowed some machines. We've installed software in those machines. Can we verify that we can talk to those machines and they can talk to each other in a way that's secure, that's cheap, that's safe? And so how this works, we've got some local machine, right? Here on my example, I'm running this notebook, this Jupyter notebook on my laptop, and I'm connecting to this remote Dask cluster sitting in the cloud over the open internet, right? And how do I verify that, for example, you can't also connect to that Dask cluster? By default, Dask connects over TCP. If you've used Dask before, you've probably seen addresses that look like this. Those addresses are fine, but they are insecure, right? And that's actually totally fine. There aren't that many people kind of hunting around the internet searching for open Dask clusters. But if you're in a secure organization, this will probably become an issue because other people could also connect to that same Dask cluster. They could be, using your credentials. They could be accessing your data. They could be, changing your data. The most common way to solve this is by using secure connections and by distributing TLS keys everywhere. The first project to do this is dask-gateway. Dask-gateway is also an excellent way to deploy Dask on Kubernetes or other systems. Dask-gateway can either proxy your connections or it can sort of broker a connection for you, again, setting up TLS everywhere. You still need to have some system that lets everybody know who the gateway is and how to trust them. So there's not some other phantom gateway pretending. This allows you to stop other machines from being able to connect to your scheduler or other workers to connect to the cluster in a nefarious way, or even other gateways trying to pretend to be the gateway. To manage all of this, you also need some kind of user database that can tell who's who. This might be Active Directory. This might be some intermediate service like Keycloak. What we often see with sort of more open sourcey groups is they use JupyterHub, which is a pretty lightweight user database system. So if you want to handle security, you have a sort of an architecture diagram that looks something like this. That's, you don't need to do this. You can stay sort of insecure for a while, and that's fine. I think many people, even at very large institutions, stay insecure for a while. So this is probably fine. But if you sort of want to go whole hog, you'll need to think about these kinds of things. So moving on to observability. So we talked about, again, borrowing machines, installing software, connecting the machines well. How about observability? So stuff broke, what happened? Right, and we saw this in my example, right? I ran some stuff, I looked at profiles, I said, this doesn't seem right. And so I sent something to my colleague, James. I sent him first this performance report, and then I made a change and I said, hey, look, here, go look at some logs. I was able to point him to a historical result, right? And it's really nice to be able to do this, right? I don't have to sort of have a live session to show him things. I can sort of point him to what's actually going on in the world. And this is really useful, right? This kind of observability thing. It helps me work with my colleagues and find something that works well for all of us. So why do we care about observability? We've seen logs. People say, hey, look, things broke. This is most of my life. Someone tells me his Dask broke, and I have to figure out what happened. Another common case, just a few weeks ago, I was talking to a large user group that doesn't use any kind of platform, or they've built their own platform. And I say, hey, look, you should upgrade to this version of Dask. The new version of Dask is way better for you. It solves lots of problems your users are facing right now. But hey, look, we actually are afraid about upgrading because our current workflows might break. We've got users who are using this thing, and we don't want to sort of break them. I say, great, let's go and assess all the active workloads and see what they're doing. And they actually had no ability to do this. They actually had no idea who was using Dask. They had no idea who was using their platform. Or they did, but it was buried somewhere they didn't have good access to. And so telemetry informs decision-making, right? Can I use new things? Can I retire things? Can I fix things that are broken? Unfortunately, Dask provides a lot of telemetry, right? So there's very basic things like logs, which any system will provide. And these should go into some kind of log aggregation service, right? Probably Datadog or CloudWatch or somewhere that you can get access to them. Dask also provides a lot of sort of performance telemetry, right? Dask has knowledge about how much money you spent parsing CSV files and how much S3 bandwidth you're using and how much internode bandwidth you're using. And this kind of information aggregated across all of your users and all the time can really inform a lot of sort of cost-cutting measures, a lot of performance tuning measures, a lot of sort of tracking who's having issues. It's really valuable. You should be tracking some of this information somewhere. A lightweight way of doing that is with Prometheus. So Dask and many other systems publish Prometheus metrics. Throwing those into a time series database and putting something like Grafana on them can really help you understand what's going on in your system across your organization. Let's see. Yeah, so telemetry saves lives, or at least debugging time. The last thing I want to mention is users and cost. The basic question people want to ask is, why am I spending money? Who's spending that money? How do I turn things off? There's a lot of waste in any large deployment that we've seen. If you go to like a customer and talking about their Databricks bill, it's like probably only 10% useful things, about 90% waste. And people, especially at large organizations, are really curious about how to make this better. The simplest question is, did I turn everything off? This is actually a source of a lot of anxiety for new users. And often you think you did, but you actually left things on. I've done this. I think everyone that I've seen use the cloud has left things on. In fact, Jacob Tomlinson, our sort of the Dask maintainer that thinks most about deployment, thinks it's probably one of the scariest problems we have today. So you want to be able to ask questions like, what's costing you money, right? How much money are we spending? So this is a trace of one of our internal benchmarking accounts, amount of money we spend per week just doing benchmarking. And there's things here that I'm curious about as a business owner, and I want to see what's going on. $500 in a day it's fine, but it's it's an FTE. I might want to attribute those costs to individual users. Here's Ian spent about a couple of compute weeks a few weeks ago in a day. What was he doing at the time? What was happening this day? Right? Was everybody off? Was the system down? You sort of want to get some more of this information. And then once you can map your trust to different users, you want to start to think about controlling those limits, right? How do you reduce that spend? How do you constrain that spend? So I just went very rapidly through a bunch of things you're going to want to think about in deploying any kind of distributed computing framework. Let's talk about some solutions, right? So we talked about some problems: borrowing machines, installing software, connecting securely, observability, and cost management. There's some platforms which solve these problems or try to solve some of these problems for you. I'm going to talk through a few of them. So I asked these folks for slides. The Nibari folks actually gave me the best slides. We're going to spend the most time with them. And then I'll talk about Coiled, which is my bias, where I work. So there's a project called QHub, which is a bunch of open source tools, including Dask, all bundled together. QHub recently rebranded to Nibari. So if you're familiar with QHub, sort of mentally shift your thinking. This comes out of a great company called Quansight, which has a lot of open source work in the community. So Nibari is a collection of open source software packages all bundled together. This includes packages like Jupyter, Prefect, Conda Management, Prometheus, Grafana, video chat service I wasn't aware of, and also Dask. And so that's why I'm talking about it today. But they do lots of things. And so you might consider them for lots of different systems. Nibari works in sort of a GitOps or infrastructure as code approach. So you provide a lot of YAML files that define the system that you want. They turn that configuration into Terraform, and they deploy that for you in whatever cloud or Kubernetes system that you have. It's a really good way to produce a nice sort of Jupyter data science scalable platform wherever you are. I'll mention a few packages inside of their system. There's Conda Store, which sort of takes Conda packages, pip packages, and serves those up as Docker images or environments. They don't serve just Jupyter. A common concern we hear is people do just Jupyter. They also provide proper IDEs for actual sort of software engineers too. And also things like dashboard development. So they sort of think about the whole development cycle. So there's Saturn, which is, I'm actually going to go through kind of, for time constraints, I'm going to go through this quickly. Saturn does mostly the same thing. They bundle up a lot of open source projects, but they do so in a more AWS focused way. Same with Kubeflow. Again, the same thing. They sort of do the same thing on Kubernetes, very Kubernetes forward. The most I want to point you out to here is that, all right, go ahead. Great. I want to point you to the Dask Kubernetes operator, which was released recently, that helps Dask become much more Kubernetes native. So if you're in Kubernetes land, think about Kubeflow, think about Nibari. If you're on AWS, think about Saturn, or think about Coiled. So I work on Coiled. A lot of Dask maintainers work on Coiled. So briefly, Coiled doesn't do what everyone else does. It doesn't bundle because a lot of different packages. Coiled thinks just about Dask. So we focus very deeply on Dask, and we allow it to integrate very well to other systems. So for example, in our example, we saw that I was playing with Jupyter on my laptop. And connecting out to Coiled, right? So Coiled doesn't have Coiled notebooks. We just allow you to use Coiled from anywhere. Same with Conda, same with Prefect, same with VS Code. Coiled is very agnostic to other technologies you use. And we do Dask very, very well. There's a lot of nuance to doing this well. We care a lot about this sort of interplay between Dask and the cloud. There's a lot of things to talk about. There's no single feature that's awesome. I'll mention a few things that users mention in the next couple of minutes. First, setup is trivial. You can conda install it from conda or pip. You can log in with GitHub or Google. Authentication is trivial. You can set up, so Coiled deploys inside of your own cloud. We don't manage your computation. We instead click the right buttons in AWS for you, and then sort of broker a connection to that system and then get out of the way. You can set up Coiled either by going to AWS console and the Coiled UI or from your command line. We actually have a pretty nice setup wizard that runs everything in about 3 minutes. Once you're there, you can run it from anywhere. Coiled is super configurable. You can have lots of different machines. And you can be actually pretty prescriptive with where you want those machines to live, what kind of machines you want, what instance types you want. And you also support colleagues that don't understand things. I'm going to pass through a bit of this quickly just because it takes some time. We used to do the same thing that everyone else does, where you can handle conda and pip packages. We actually found this was kind of a pain in the butt. It's really hard to specify your environment. This changes pretty frequently, we found. And so we've actually shifted to this thing called package sync, which just looks at your local environment, packages it up, and ships it remotely, all in about as fast as you can do a Docker pull. It's actually a really nice piece of technology. We're pretty proud of it. Yeah, I'll move past. Finally, costs. There's actually a big point of contention among users, apparently. And Coiled has a lot of cost-saving measures. I'll bring up one here, which is spot instances types. So this is a time series showing a usage, I think, one of our internal accounts. And the blue is our usage of spot, and the orange is our usage of on-demand. So we run workflows on a regular basis. We need them to run. We want to use as much spot as we can, but fall back to on-demand. This feature is actually really well loved to be able to sort of use spot when you can, but fall back to on-demand when you can't. And you can see we're actually getting a nice blend most of the time. And this actually results in us having far lower costs. We'll do things like gracefully shut workers down when responses go away, or choosing the right zone where there's the most spot that's available. There's a dozen other cost-saving measures I can mention, but this is one. It's neat. It's a good example of knowing Dask and the cloud well and that interplay and being able to handle that well. So that's it. Yeah, zooming back out. Dask is easy. Deploying it is easy until it's not. Thanks for your time.